This is my Calculus 1 course. Today we're going to learn differentiation formulas. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So, in the previous class, we learned how to find the derivative function, but you may have noticed that it wasn't so easy. We had to use this formula, the derivative formula, and the algebra was kind of tedious. It took a while to find the function, but the good news is that we don't really have to use this formula every time we want to find a derivative. We can use shortcuts, and we're going to learn those shortcuts today. But before we do that, we need to learn some alternate notation for the derivative. In the previous class, we learned this notation. But sometimes a function is going to be defined, or it's going to be named y. For example, you might have y is equal to x squared plus 3x. And so when we find the derivative, we often call it y prime. Or we use something called Leibniz notation. This is Leibniz notation, created by a guy named Gottfried Leibniz. And so we can call the derivative of this function dy over dx. This notation is, well, it has some positive things about it and some negative things. One thing that's not very desirable is this looks like a fraction. It's not really a fraction. You can think of it as a fraction in some contexts in the future parts of the calculus curriculum, but for now we don't really consider it to be a fraction. But it looks like a fraction, so it's kind of confusing. But there are some good things about this notation, and so we use the notation in many different scenarios. One good thing about this notation is that we identify the dependent variable, which is y, and the independent variable, which is x, in the notation. So we identify both variables. If we want to identify the actual expression that we're finding the derivative of, we use a different variation of Leibniz notation. Leibniz notation has a lot of different variations. So if we know what f of x is, for example down here, you see these yellow expressions, we know the function that we're trying to find the derivative of, or the subsequent derivative function. In those situations, we use this notation up here. And so this notation is useful because it indicates two things. Number one, we're finding the derivative of the function, and number two, we're identifying which function we're finding the derivative of. And these green expressions are the derivative functions of the corresponding yellow functions. So the way that you read this is the derivative of x squared is 2x. The derivative of the square root of x is equal to 1 over 2 times the square root of x. The derivative of 1 over 3x is equal to negative 1 over 3x squared. That's how you read that notation. So this notation just means we're finding the derivative of the orange expression, and the result is this purple expression. So we're going to use that notation when presenting the differentiation formulas. So these are the shortcut formulas that we use when we actually apply calculus. And you see we have Leibniz notation. So I want you to get a picture of these formulas. Today we're probably going to only have time to do the first three formulas. But you should have a picture of those formulas. Before we start using the formulas, I'm going to show you some proofs. But real quickly, just to explain, let's say that f of x is equal to some constant like 3. Then the derivative would be 0. The derivative of a constant is always 0. That's differentiation formula number 1. And the reason for that is that if you graph a constant function like f of x is equal to 3, it just looks like a horizontal line. And remember, the derivative is the rate of change of the y values as the x values change, but the y values are not changing. The y values are all the same if you look at the points on this line. So the rate of change of the function is 0. Remember, we also think of the derivative as the slope. It's the slope of the tangent line to the curve. Even though this is a line, we still call it a curve. And remember, if you have a flat line, the slope of the line is just 0. So the derivative of a constant function is 0. So c we consider to be a constant. We have another very important formula here. The derivative of a power function is given by this formula here. So what this means is that if our function is equal to x to the 5th power, for example, then the derivative function is 5x to the 4th power. So I use this formula here instead of using the formula that we learned in the previous class, which is really long and tedious to have to show that. We use this formula here. So it's much, much faster. So that's the power rule. And the constant multiple rule tells us that if we have a constant times some function, for example, if f of x is equal to -5 times x cubed, the derivative is just equal to that constant times whatever the derivative of x cubed is. So again, this is Leibniz notation. This means that we're finding the derivative of x cubed and then multiplying it by 5. So here's a proof of the constant rule. We don't really need to go over this in detail, but we don't really need to prove it because we know that the derivative of a constant function has to be 0. It's just a flat line. But if you wanted to plug it into the derivative formula and prove that the derivative is 0, you can see this is the logic behind that. And this is a proof of the constant multiple rule. If we have some function that's equal to a constant times another function, and again, for example, we might have g of x is equal to -10x squared. That would be an example. So -10 would be the constant, and f of x will be x squared. So this is an explanation of why that rule works. We don't have to go over this in detail right now because it's more important that we just learn how the formula works. But if you want to know why that constant multiple rule works, there's the explanation. And one of the most important rules that we need to learn is like I said, the power rule. And here's the proof of the power rule. So let's say that if you have some function f of x is equal to x to the n power, then the derivative of that is n times x to the n minus 1 power. And this is the proof of that. So in order to prove that that's true, we have to use the derivative formula as we used in the previous class. And this is f of x is the blue, and h we just rewrite. But f of x plus h is exactly the same as the blue expression. Instead of x, we write x plus h. But we have to expand that expression, and that's why we learned the binomial theorem in the previous course. in my pre-calculus curriculum, and that's one of the reasons that Isaac Newton spent so much time studying the binomial theorem, is he wanted to come up with this derivative rule when he discovered calculus. So as you can see, the yellow expression, if we use the binomial theorem, the yellow expression ends up looking like this. Now, it's been a while since we've seen combinatorics notation, but if you want to know what the green, purple, and pink expressions are, you would use this formula over here. And again, we could spend 20 minutes going over this, but I don't want to spend a lot of time doing this. But the reason that you learn the binomial theorem is to prove this particular differentiation formula. So remember, we say n choose 0. How many ways can you choose 0 things out of n things? Well, that's just defined to be 1. It doesn't really make any sense, but it's defined to be 1. How many ways can you choose 1 thing out of n things? Well, that's just n, obviously. That makes sense. And then here we just kind of wrote this expression in a different form. Again, if you want to know why that's true, you can use this formula here. So I don't want to scare you by showing you this. This is not really the purpose of this class today, but this is just the proof of the formula. So if you keep going, you see that these expressions cancel out, and then when we divide by h, because at this point, if we plug in 0 for h, we still have 0 divided by 0. The h's, well, the h will cancel out in the first term, and these h's will be reduced by 1. But after you divide by h, you can allow h to be 0, and all these terms cancel out except the first one. So that is the proof of the power rule. But again, none of that really means anything unless we understand what's important about these rules. So again, get a picture of the differentiation formulas, and you can look over that proof if you want, but what's most important is that we actually know how to do this math. So we can go back to those proofs and look at them a little more in the future, but for now we need to see why we even care about these proofs in the first place. So let's do some problems. We have a function, and this is a constant function, so f prime of x is 0. We're looking for f prime of x. Because it's a constant function, the derivative is just equal to 0. So that is differentiation formula number 1. All right. So now we're given another function and asked to find f prime of x. So in this case, we use differentiation formula number 2. And if you don't have these formulas written down, or if you don't have a picture, you need to take a picture of these. I'm going to give you one last chance to take a picture of these formulas. So far we used formula number 1, and now we're about to use formula number 2. So that formula tells us that we bring the exponent down, and then we reduce, or we subtract 1 from the exponent. So the new exponent is 1 less. So that is the derivative. So as you can see, this is a lot easier than using that formula in the previous class. Okay, so let's find the derivative of this expression. We're going to have to use the constant multiple rule, which is differentiation formula number 3. And that tells us that if a function is equal to a constant times some other function, then the derivative is the constant times the derivative of the other function. Now notice we're using Leibniz notation, that means we're finding the derivative of x to the 12th power. But at this point, we have to use differentiation formula number 2, which is the power rule. So we bring 12 down in the front, and we subtract 1 from the exponent. Multiply -3 and 12, and we get -36. And then subtract 1 from the exponent, we get x to the 11th. So as you can see, this is really not that difficult. It's a lot easier than the formula we used in the previous class. So now we're going to use a different type of notation, but we're just doing the same thing. We're using different notation because now our function is named y. That's the y represents the output to the function. So now we're looking for dy over dx, and that's just 0, because 2/7 is just a constant. So we used differentiation formula number 1. These could also be called derivative formulas. Okay, and now we're going to find the derivative again, but we're calling it dy over dx, and we're going to use the power rule, differentiation formula number 2, which tells us that we bring that power down in front, it becomes a coefficient, and we subtract 1 from the exponent. So we have 6 times x to the 5th power. There you go. It's that quick. Alright, so you're not going to have to show all these steps. In fact, you don't really have to show any of those steps. I just want you to be aware, if you get comfortable with this stuff, you don't have to show any of these steps. You can just go right to the answer. The purpose of showing you these steps is just to show you how the formulas work. So again, we're trying to find dy over dx, which is the derivative. But now we're going to have to use the constant multiple rule, because we have a constant multiplied into some function. So that's differentiation formula number 3, which tells us that the derivative is the constant times the derivative of whatever function is multiplied into the constant. Then we're going to use differentiation formula number 2, the product rule, which tells us that the derivative of x to the 8th power is 8 times x to the 8 minus 1 power. So we bring the exponent in front as a coefficient, and we subtract 1 from the exponent. So now we can multiply 10 times 8 is 80, and 8 minus 1 is 7. So there you go. Okay, so let's try a couple more problems before you try one on your own. But now we're going to use y prime notation. It's the same thing, it's just the derivative, and e squared is a constant. Remember, we learned that constant e, I think it's 2.71, and it just keeps going on and on and on. That's Euler's number. That's why we use an e to notate it. It's an irrational number, but it's nonetheless a constant. So the derivative of e squared would just be 0. So we used differentiation formula number 1. Okay, so let's find the derivative of this function here. We're just going to use the power rule. That is differentiation formula number 2. So we have 9 times x to the 9 minus 1, which is 9 times x to the 8th power. So this stuff really is not difficult at all. It's very simple. We're just getting used to these formulas. So now we're going to find the derivative of this expression here. We're going to have to use the constant multiple rule. That is rule number 3. Or differentiation formula number 3. And so we have negative 7 times the derivative of x to the fourth, which is 4 times x to the 4 minus 1 power. Again, you don't have to show this intermediate step if you don't want to. Negative 7 times 4 is negative 28, and then we have x to the third power. So there you go. So that is how this stuff works. I'm going to give you one more chance to take a picture of these differentiation formulas. We're mostly going to be using the first three formulas. And you can take a picture of all the problems that we did here, numbers 1 through 5, and take a picture of problems 6 through 9, or you can just leave those in the window. So I want you to try problem number 10. And when you come back, we'll do it together. Okay, we're back. So we're looking for the derivative. The derivative of any constant is just 0. That was differentiation formula number 1. So if you got that right, good. Try number 11. When you come back, we'll do it together. All right, we're back. So if you got that right, good. Go ahead and try number 12. You're going to need the constant multiple rule. And when you come back, we'll do it together. All right, we're back. And we get 15x squared. So there you go. If you got that right, excellent. So we use the constant multiple rule, differentiation formula number 3. And then we use the power rule, which is differentiation formula number 2. Okay, so now we're changing to dy over dx notation, but that's just the same thing as f prime of x. All right, we're just finding the derivative function. So try number 13. When you come back, we'll do it together. Okay, we're back. So the derivative is 0. That's just formula number 1, because negative 0.4 is just a constant. The derivative of any constant is just 0. So if you got that right, good. Try number 14. When you come back, we'll do it together. All right, we're back. So that is the power rule, differentiation formula number 2. So if you got that right, excellent. Go ahead and try number 15. You're going to use the constant multiple rule. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. So you can take a picture of these problems if you'd like. And now we're changing to a different type of notation, y prime. But it's the same thing that we've been doing before. It's just another notation for the derivative of the function. Try number 16. When you come back, we'll do it together. All right, we're back. So y prime is 0, because this is just a constant. You're subtracting 2 from this expression, but it's still just a constant. You have a constant, subtract 2, you still have a constant. So that was kind of a tricky one, but it's just 0. The derivative is just 0. So go ahead and try number 17. And when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So that was an introduction into the first 3 differentiation formulas, or derivative formulas. You can call them derivative formulas or differentiation formulas, whatever you want to call them. Now we're going to move on to some problems that are really just the same thing, just with a few tricks. We don't know how to find the derivative of this. We just can't do it. We don't know any formulas at this point. We could use some of the formulas on the list, but we haven't learned any formula past the third. We've learned the first, second, and third. We haven't learned how to do the other ones. But we can still find the derivative by using the the formula number 2, the power rule. All we have to do is change the form of that expression to x to the negative fifth power. The power rule works for really any number, as long as it's a real number. So it doesn't matter if it's negative or a fraction or whatever. So I want you to understand very clearly we have not found the derivative yet. All we did was just change the form of this expression. Now how can we do that? Well, that's exponent rule. Remember the exponent rules we learned in intermediate algebra? That's exponent rule number 8. Just going backwards. So now we can find the derivative. We just use differentiation formula number 2, the power rule. And so we have negative 5x to the negative 5 minus 1 power. So negative 5 times x to the negative 6 power. So it's that simple. But in my curriculum, I don't want you to leave your answer with negative exponents. So we're now going to use exponent rule number 8 again, but we're going to change that to a positive exponent where we're going in the opposite direction. And the final answer is negative 5 over x to the 6th power. The reason that I don't want you to leave it in this form is because negative exponents really don't have any direct meaning. They have to be interpreted. So we're interpreting by changing to this final form. Okay, so I want you to try a problem like that. It's very easy. All you have to do is change to a negative exponent. So I want you to try number 20. And you can use number 19 to help you. So when you come back, we'll do it together. Okay, we're back. So before we do anything, we're going to change this expression to x to the negative 10th power. Negative exponents don't have any direct meaning. Okay, so there you go. Again, that was exponent rule number 8 that we had to use, and the power rule. So if you got that right, excellent. So now we have another type of problem, which is just a kind of a slight variation. The only difference with this problem is we have a constant up here. So we have to use the constant multiple rule. So before we change, or before we find the derivative, we're going to change the form of this expression. So I'm going to change the expression to negative 6 times that fraction. And we can write negative 6 as negative 6 over 1. And remember, when you multiply fractions, you just multiply straight across. So negative 6 times 1 is negative 6, and 1 times x to the 8th power is x to the 8th power. So that's just basic math. So I factored the negative 6 out, and then I'm going to use exponent rule 8 to change that expression to x to the negative 8th power. At this point, we're ready to take the derivative. We could not take the derivative in this form because we don't know how. We haven't learned how to do that yet. So now we're going to find the derivative, and we're going to use the constant multiple rule, which tells us that the derivative is equal to the constant times the derivative of whatever function is multiplied by the constant. So that is differentiation formula number 3, the constant multiple rule. So now we have to use the power rule, differentiation formula number 2, in order to find the derivative of x to the negative 8th power. So that's negative 8 times x to the negative 8 minus 1. Negative 6 times negative 8 is 48. We have x to the negative 9th power. And again, some teachers may allow you to leave the expression in that form, but we really shouldn't be doing that because it has no direct meaning. So I'm going to use exponent rule number 8 to change that to 1 over x to the 9th, and then we can write our final form, 48 over x to the 9th power. So there you go. I want you to try a problem like that, but first get a picture of these problems, especially number 21. Number 21 is going to help you with number 22. So go ahead and try number 22. When you come back, we'll do it together. Alright, we're back. So we get negative 12 over x to the 7th power, rectangle, and there you go. Alright, so if you got that right, perfect. Okay, so now we have a very similar problem, except there's a coefficient in the denominator as opposed to the numerator. Before we do anything, we're going to change the form of the expression. So I'm going to factor 1/6 out. And isn't it true that if you multiply these fractions, you get 1 over 6x squared? Because you multiply the numerators, you get 1. Multiply the denominators, you get 6x squared. That's how we multiply fractions. So I factored out 1/6, and now I'm going to change 1 over x squared to x to the negative 2 power. And now we're ready to find the derivative. So the derivative is 1/6 times whatever the derivative of x to the negative 2 power is. So that is the constant multiple rule. And I noticed I put y prime. Sorry about that. That was supposed to be dy over dx. It's the same thing. It's just we're told to find dy over dx, so we should use that notation. So now we're going to use the power rule, differentiation formula number 2, which tells us that the derivative of that expression is negative 2 times x to the negative 2 minus 1, which is negative 1/3 times x to the negative 3. And then we're going to change the form of that expression using exponent rule number 8. And the final answer, if we multiply those fractions, is negative 1 over 3x cubed. So there you go. That's just another variation of these problems. The constant rule and the constant multiple rule and the power rules are some of the most important formulas that we're going to use in this entire course. So it's not enough for you to just have a familiarity with these formulas. You need to know them like the back of your hand. So try number 24, and when you come back, we'll do it together. Alright, we're back. Over 2x to the 4th power. So now we're going to go to a different type of problem, but we're still just finding derivatives. Now we have a square root expression. We don't know how to find the derivative of a square root expression, but we can change the form of that expression to x to the 1/2 power. That's exponent rule number 9. And now we can use the power rule. So again, that is differentiation formula number 2. So now we have 1/2 times x to the negative 1/2 power. 1/2 minus 1 is negative 1/2. And we have two issues here. We have a negative exponent, and we also have a fraction exponent. fraction exponents and negative exponents don't have any direct meaning, so we have to interpret that expression. First, we need to deal with the negative exponent, so we're going to bring the expression down, and the exponent becomes positive. So we dealt with the negative exponent, but now we have a fraction exponent that we still have to deal with. Exponent rule number 9 tells us that that expression is equal to 1 over the square root of x. That's exponent rule number 9, and then we can multiply the fractions and we get 1 over 2 root x. Now, if you recall, in the previous class we actually found the derivative function, the derivative of this function here, using this formula, but that took a lot of time. So as you can see, using this math here is a lot quicker. And I want to stress that you're not required to show this step or this step. You can skip a lot of these steps. I'm just showing every step just so you know what we're doing. Okay, so let's try another one of those problems before you try one on your own. So now we're going to find dy over dx, but first let's rewrite the expression as x to the 1/6 power. Again, that is exponent rule number 9. So now we can find the derivative. And I got to remember to write dy over dx. That's equal to 1/6 times x to the 1/6 minus 1 power. Again, using the power rule, differentiation formula number 2. So we have 1/6 times x to the negative 5/6 power. And again, we have two problems. Our first problem is we have a negative exponent. So we'll deal with that with exponent rule number 8. And our second problem is we have a fraction exponent. We'll deal with that with exponent rule number 10. So number 10 tells us that that becomes the 6th root of x to the 5th power. You can also write it as the 6th root of x all raised to the 5th power. It's the same expression, just a different form. So we can write our final answer as one fraction, 1 over 6 times the 6th root of x to the 5th. Try number 27. When you come back, we'll do it together. Okay, we're back. So first we're going to change the form of the expression. So if you got that right, excellent. Okay, so now we have a similar problem here. We just have a coefficient, and we're going to be using exponent rule number 10 from the start. But before we find the derivative, we need to change the form of the expression. So we're going to change that to x to the 7/4. That's exponent rule number 10. Okay, so now we're going to find the derivative using the constant multiple rule, differentiation formula number 3. So we get 10 times whatever the derivative of that function is. And to find the derivative of that function, we have to use the power rule, so we bring the exponent down in front. And we subtract 1 from the exponent to find our new exponent. So now we have negative 70 over 4 times x to the 3/4 power. And we can reduce this fraction. That becomes negative 35 over 2, it looks like. And now we have to use exponent rule number 10 again. X to the 3/4 power is the fourth root of x to the third power. That's what that actually means. So I want you to try a problem like that. Get a picture of number 28. That'll help you. And I want you to try number 29. So when you come back, we'll do it together. We have to change to root x using exponent rule number 9. So if you got that right, excellent. If you got stuck in a few places, that's okay. We're learning this for the first time, so here's a different type of problem. Again, we're just going to do a little bit of algebra before we find the derivative. We don't know how to find the derivative of this. We're going to learn how to find the derivative of this expression directly in future classes, but today we need to change the form of this expression. We don't know how to find the derivative of that. So what we're going to do is use exponent rule number 3. I wrote these letters a little differently. I chose different letters than the rules that I give you in my intermediate algebra course, just because we're using y and x here and I don't want things to get confusing. But what this rule tells us is that we can change that expression to 3 to the third power times x to the third power. So we have 27 times x to the third power. Now we can use our differentiation rules, specifically the constant multiple rule. And then of course we're going to use the second differentiation formula, which is the power rule. Three times 27 is 81, and we have x to the second power. So just another type of problem that you might see. I want you to try number 31. Use 30 to help you. When you come back, we'll do it together. And we have x to the 4th power, so that's the answer. If you got that right, very good. Excellent. Okay, so here's another variation of a problem that you might see. We don't know how to find the derivative of that because it's a function inside another function. We haven't learned how to find the derivative of that yet. So we're going to use exponent rule number 4, which tells us that the expression becomes x squared over 7 squared, which is x squared over 49. Now, this really causes a lot of problems for students. Really causes a lot of problems. Because we have a fraction and students don't know how to find the derivative of a fraction, but that's okay because we can just take the 1 over 49 out and treat it as a constant. So now we can find the derivative using the constant multiple rule, or the constant multiple differentiation formula. So the derivative of a constant times a function is just the constant times the derivative of whatever the function is. So then we can use the product rule, and we have 1 over 49 times the derivative of x squared, and we get 1 over 49 times 2 times x to the 1 power. And then multiplying, we get 2 over 49, and then x to the 1 power is just x. That's exponent rule number 6, if I remember correctly, from my intermediate algebra course. So I want you to try number 33, and when you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. So let's go on to another variation of these types of problems. So we have a function inside another function. We don't know how to find the derivative of that. But we can use our root property here, very important property, to change the form of this expression to the cube root of 5 times the cube root of x. We don't have to write a dot there, but it just helps to show that we're multiplying. If you don't have a dot there, mathematicians still understand that that's multiplication. Well, now we're going to change the expression using exponent rule number 9, so that becomes x to the 1/3 power. And now we're ready to find the derivative. So derivative is the cube root of 5 times the derivative of whatever that function is. And then, of course, we're going to use the power rule, differentiation formula number 2, which tells us to bring down the exponent and then subtract 1 from the previous exponent, and we get the cube root of 5 over 3. If we multiply those together, 1/3 times the cube root of 5 times x to the negative 2/3 power. 1/3 minus 1 is negative 2/3. But we're not allowed to leave our exponent as a negative fraction. First we'll deal with the negative part of the exponent. We'll bring it down. And then we'll deal with the fraction part of the exponent. We'll change it to 1 over the cube root of x squared. But we can continue a little bit more. And put these together. We can make it the cube root of 5 over 3 times the cube root of x squared. We could simplify that even more if we wanted to. We could combine that to one big cube root, but we're out of room, and it's not really necessary. So I'm going to leave it in that form there. So I want you to try number 35, and when you come back, we'll do it together. Okay, we're back. So we're going to rewrite the expression before we do anything. So f of x is equal to the square root of 7 times the square root of x. That's this principle up here. The case where n is equal to 2. Again, we don't see 2 in the index. You see this, the blue 2? It's there, we just don't write it. Over 2 times the square root of x, and we could combine these square roots to make a slightly more simplified answer, but it's not really necessary at this point, and we don't have enough room anyway. So if you got that right, excellent. So we're doing two things now. We are learning the differentiation formulas, and we're also reviewing rules with roots and exponents. So here we have another situation. We want to find the derivative, but we can't because we don't know how to deal with fractions. But we can rewrite this expression as 1 over x to the 3/4 power. That's exponent rule number 10. Alright, We can then rewrite it as x to the negative 3/4. That's exponent rule number 8. So now we can find the derivative using the power rule differentiation formula number 2. So then we get negative 3/4 x to the negative 3/4 minus 1, which is negative 3/4 times x to the negative 7/4. We don't like negatives in the exponents, so we're going to change to 1 over x to the positive 7/4. And we don't like fractions as exponents, so we're going to change that to 1 over the 4th root of x to the 7th. And we're going to simplify that a little bit more. And we'll have our answer. So we can write negative 3 over 4 times the 4th root of x to the 7th. So let me make some more room here. And that's our final answer. Now notice that there is a root in the denominator. Normally we're not allowed to have roots in denominators, but we don't really know what x is, and so we don't really know if we need to rationalize the denominator, because we don't know if the denominator is even an irrational number. It probably is, but we don't want to get bogged down with rationalizing denominators. It's not something that's really required when you have variables. It technically, some teachers may require you to do that, but most teachers probably will not, because it just distracts from the point of this class. So we used exponent rule number 10 in that problem. Now we're going to use exponent rule number 10 again. Before we find the derivative, we're going to factor out 9. So we're just changing the form of the expression. And then we're going to use exponent rule number 10 to change that to 1 over x to the 6/5. This is a little bit different. It's written in a different form, but it's still the same as this form, just the same value, but written in a different form. What I mean is it's the same value, not the same form. It's the same value, different form. So now we're going to use exponent rule number 8 and bring that up to x to the negative 6/5 power. And now we're ready to find the derivative. So the nature of these problems are such that it's just easier to change the form of the expression if you're looking for the derivative. So we're going to use the constant multiple rule, differentiation formula number 3. And then when we take the derivative of x to the negative 6/5, we're going to use the power rule, exponent rule number 2. And then we get 54 over 5 times x to the negative 11 over 5 power. So that's the derivative. We're pretty much done, except again we need to write our final answer as something that we can actually understand. So we're going to use exponent rule number 8 and convert the exponent to a positive exponent. And then we're going to use exponent rule number 10 and convert that to 1 over the 5th root of x to the 11th power. And we can do maybe one more step if we want to. It's not really that important to write it in the simplest form in this particular context. But normally when you check the answers in the back of textbooks, they're going to have their solution in the simplest form, so you need to be prepared to verify your answer is correct by converting your answer to simplest form, the simplest form possible. Okay, I just realized that I was using the wrong, it's not wrong, but we're supposed to find dy over dx. I was using y prime, so sorry about that. It's not wrong, it's just we prefer to use the notation that they tell us to use. But you're gonna use y prime notation, so go ahead and try number 38. 36 and 37 will help you, and when you come back we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 39. When you come back, we'll do it together. Okay, we're back. So if I got that right, excellent. Again, we don't really care about rationalizing the denominator with these problems because that would just make this even more complicated. Okay, so let's try these problems together. We're going to find f prime of x. Again, this whole class is just about finding derivatives, so the answer is 0. Why is the answer 0? Because it's a constant. So that was exponent rule, or that was differentiation rule number 1. Now for this problem, we certainly don't know how to find the derivative of that. That expression is too complicated. But we can change the form of the expression. We can use exponent rule number 6 to change that to x to the 1st power. Then exponent rule number 9 to change that to x to the 1/2 power. Then we can use exponent rule number 1 to change that to x to the 1 plus 1/2 power, which is x to the 3/2 power. Now we can find the derivative using the power rule. So we have 3 over 2 times x to the 3 over 2 minus 1 power, which is 3 over 2 times x to the 1/2 power. Then we can use exponent rule number 9 to change that to 3/2 square root x. And then we're done. So again, that was the power rule that we used here. Okay, so let's try another one of these. We don't know how to find the derivative function of this function here. It's just too complicated. So we're going to use the exponent rules. We're going to change that expression to x to the 5/4 power. And then we're going to use exponent rule number 1. Again, when you're multiplying powers, you add the exponents. So we have 2x to the 3 plus 5 over 4 power, which is x to the 17 over 4 power. So now we're ready to find the derivative. We're going to use the constant multiple rule. We have 2 times the derivative of that function. So we have 2 times, using the power rule, 2 times 17 over 4 times x to the 17 over 4 minus 1 power. Then we get 17 over 2 times x to the 13 over 4 power, and using exponent rule number 10, we get the fourth root of x to the 13th power. So that's just another type of problem there. So again, we're finding derivatives, and we have to change the form of the expressions before we can find the derivative. So here's one more example before you try one on your own. We're going to change these expressions to x to the first power, that's exponent rule number 6. We're going to change to x to the 1/3 power in the denominator, that's exponent rule number 9. Now we're going to use exponent rule number 2, which means that if we divide powers, we subtract the exponents. So we get x to the 2/3 power, and now we're ready to find the derivative. Using the power rule, we have 2/3 x to the 2/3 minus 1 power, 2/3 times x to the negative 1/3 power, but we don't want to leave our answer with a negative fraction exponent. So we're going to reduce to 1 over x to the 1/3 power, or not reduce, but change the form. But we have a fraction power. We don't want the fraction power, so we're going to change to 1 over the cube root of x, that's exponent rule number 9. And then we can write our final answer as 2 over 3 times the cube root of x. Sorry, we're kind of scrunched in there. So those are 3 problems that kind of had the same type of theme. I want you to do number 44. 44 is, well, see if you can figure it out. When you come back, we'll do it together. Okay, we're back, so we want to find the derivative of that function. The derivative is 0. Because pi is a constant, if you raise it to the 8th power, it's still a constant. So it's kind of a trick problem. That's differentiation formula number 1. Alright, so go ahead and try number 45. When you come back, we'll do it together. And there you go. So if you got that right, excellent. Go ahead and try number 46. When you come back, we'll do it together. Okay, we're back. So that is the derivative. So if you got that answer, excellent. So go ahead and try number 47. When you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. Okay, so those are just some more problems. We have a few more problems. We saw the multiplication version of this root principle here. Now we're going to use the division principle. Again, we don't know how to find the derivative of that expression, so we're going to use this principle up here and change that to the square root of x over the square root of 6. Then we're going to factor out 1 over the square root of 6. Then we're going to change the square root of x to x to the 1/2 power using exponent rule number 9. At that point, we're ready to use the constant multiple rule. which tells us the derivative of a constant times a function is the constant times the derivative of the function. Then of course we're going to use the power rule, differentiation formula number 2, and we get 1 over root 6 times 1/2 times x to the 1/2 minus 1, which is 1 over 2 root 6 times x to the negative 1/2. And we don't like negative exponents, so we're going to change that to 1 over x to the positive 1/2. And let me find a little more room here. And now we can write 1 over 2 root 6 times 1 over the square root of x. That's exponent rule number 9. Now remember this formula up here. We can reverse the order and combine to 1 square root. Actually, I should write that principle works for any roots. So nth root, nth root, nth root. Works for any root. Did I say square root? It works for any nth root as well as square root. So what that means is you can put these together if you want. It's not really that important for today's class that you make minor changes like that, but you can put those together if we multiply the fraction. So use number 48 to help you do number 49. When you come back, we'll do it together. Alright, we're back. But just so you know, you can combine because we have 6 roots, so you can put those together. And we get 1 over 6 times the 6th root of 2x to the 5th power. So there you go. So if you got that right, excellent. So now we're going to do some special problems. What if we want to find the derivative of x? What is that? Well, technically this is in mx plus b form, this function. So we know the derivative is going to be whatever m is. M in this case is 1, b is 0. So we know the derivative is going to be 1, because the derivative, again, is the slope of a line. And when you're dealing with a curve, it's the slope of the tangent line. So we know the derivative is 1, but can we use something to help us remember that? Well, yeah, we can use the power rule. Let's rewrite this as x to the first power using exponent rule number 6. And then if we find the derivative of that, we just bring the 1 down in front, and then we subtract 1 from the exponent, and we get 1 times x to the 0 power. And exponent rule number 7 tells us that anything raised to the 0 power is just 1, so we get 1. Long story short, the derivative of x is just 1. That's something you're going to have to memorize, or you can use this every time you want to find the derivative of x, but you're going to find the derivative of x so many times that it's just going to become like second nature. You're just going to know that it's equal to 1. So that was a special case. Now here we have the same case, except we just have a coefficient. Again, if you were to write this in slope-intercept form, it already is in slope-intercept form. M is equal to 8 and b is equal to 0. But we can rewrite this as 8x to the first power. And now we can use the constant multiple rule. And by the way, I forgot to write the power rule up here. That's differentiation formula number 2. So we're going to use the constant multiple rule, which tells us the derivative of a constant times a function is equal to the constant times the derivative of whatever the function is. Now we're going to use the power rule, differentiation formula number 2. So we have 1 times x to the 1 minus 1. 8 times 1 is 8. 1 minus 1 is 0. Now we can use exponent rule number 7. Anything raised to the 0 power is 1, so we just get 8. So that's what we would expect, because in slope-intercept form we can see that the slope is just going to be 8. So I want you to use number 50 and number 51 to do number 52. You don't have to show all this work if you don't want to. You can just write the answer. It's up to you. So try number 52. When you come back, we'll do it together. All right, we're back. And we get -7. So the derivative of this function is -7. It's a constant. We're not taking the derivative of a constant. We're taking the derivative of a function, and the derivative just happens to be a constant. So try number 53. When you come back, we'll do it together. All right, we're back. That's what we would expect, because again, this expression is a linear equation written in slope-intercept form, which is mx plus b. So m is 1/2, b is 0. The slope is 1/2, so the derivative should be 1/2. Okay, so now we're going to practice differentiation formulas number 4 and 5. And these formulas basically tell you that if you have a function that is the sum of 2 expressions, then the derivative of the function is just the derivative of the first expression plus the derivative of the second expression. And I'm going to go back to the differentiation formulas and give you a chance to take pictures of those. Here's formula number 4 and number 5. Those are the ones that we're going to use now. So again, the derivative of an expression that's the sum of 2 expressions is equal to the derivative of the first expression plus the derivative of the second expression. So all it means is that if you have a sum and you want to take or find the derivative of that sum, you just take the derivative of each individual term and then add them together. So here is the proof of that. If we let r of x equal f of x plus g of x, an example might be f of x would be 2x cubed, and g of x might be 4x. In order to find the derivative, we use our formula that we learned in the previous class. So the limit of r of x plus h minus r of x over h as h approaches 0. But r of x is f of x plus g of x. So we plug it in there, and r of x plus h is the same thing as r of x, just with x plus h substituted for x. So we don't really have to go over this in detail. Students are not really required to know these types of proofs, but if you want to look over that, you can see that as we group the terms together, we can separate through fraction decomposition and then use limit law number 1. And down here we have these familiar formulas, which are the derivative of f of x and the derivative of g of x. So we proved that the derivative of a sum of expressions is the derivative of each expression added up. So that looks really complicated, but again, you're not really required to know that. That's just the proof if you want to look at that. So here we have a sum of two expressions. We can't simplify the expression anymore because they're unlike terms. They have different exponents. So how do we find the derivative, f prime? Well, we just take the derivative of each term, or find the derivative of each term, and add up the result, and you're done. Now, I didn't show the intermediate steps there. We had used the power rule here and the constant multiple rule with the power rule on this term. But if you start to show, if you start to write the Roman numeral of each rule, it starts to get really tedious, and if you have to write each step, it gets tedious. So you can really just jump down to here. So we took the derivative of this function and derivative of this function, and we added them together. That's the sum rule. It just means you can find the derivative of each term and then keep the result in the sum. It also works if you have a sum of more than two terms. The logic follows for pretty obvious reasons if you wanted to prove that, but again, and find the derivative of the first term, which is negative 32x to the third power, derivative of the next term, which is 6x to the fifth power, and derivative of the last term, which is 0, because negative 7 is a constant. So f prime of x is simply negative 32x to the third power plus 6x to the fifth power. Now, again, I'm jumping forward. I'm not showing every single step here like we did in the previous problems, because once you get to problems that are this complicated, it starts to get very tedious. So we showed many examples where we explained the steps, but at this point you should be ready to simply do these without showing every single step, especially given the fact that we have so many terms that we have to deal with. So again, let's find the derivative. We're going to use the power rule on the first term. We're going to use the power rule on the second term. Then we're going to use the constant multiple rule with the power rule, and then again we're going to use the constant multiple rule with the power rule, and then rule number 1, which says that that's 0. And I'm not going to rewrite the whole thing because that would take too long. But derivative of 22 is just 0. So you take the derivative of each of the terms in the sum and you just add them together. So I'm going to give you a chance to take pictures. Well, you can just leave everything in the window here and try number 57. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Try number 58. When you come back, we'll do it together. All right, we're back. 0 because pi is a constant. So if you got that right, good. Again, we're using the constant multiple rule, the rule number 1, the constant rule, rule number 2, the power rule, and we're combining all those. We're using those rules with the sum rule. So try number 59. When you come back, we'll do it together. All right, we're back. So because again, it's just a constant. So if you got that right, excellent. Whoops, I forgot to rectangle that. So you can see the sum rule is pretty easy. So let's do a few more problems here. Now we have to change the form of these expressions before we can find the derivative. So we're going to change that to x to the 1/7 power. We're going to change that to x to the negative 6 power. And e to the third power is just a constant. I'm going to take the derivative using all of our rules. Then we get 2/7 x to the negative 6/7, and then minus 6x to the negative 7th, and the derivative of e cubed again is just 0. Okay, so now we have to simplify, or not really simplify, but we just have to write that in a form that we can understand. So that's going to be 2 over 7 times the 7th root of x to the 6th power minus 6 over x to the 7th power. So some teachers would probably just say, forget about it. You can just leave it as a negative exponent, but it's really not. It's really informal to leave expressions with negative exponents. Whoops, forgot my 6th power there. Okay, so let's try another one of these. That was more difficult because we had to change the form of the expressions before we took the derivative or found the derivative. So let's change the form again. We need to do that in order to find the derivative. And then we have x to the 9 over 4 minus 10. So now we're ready to find the derivative. And it's going to be negative 6 x to the negative 3rd power minus, actually plus 3/5 x to the negative 4th power, and then minus 9/4 x to the 5/4 power, and then again the derivative of 10 is 0. So now all we have to do is write in a recognizable form, and I think we're going to have to write this off to the side to make more room. That's okay. So we're going to write negative 6 over x cubed plus 3 over 5x to the 4th minus 9/4 times the 4th root of x to the 5th power, and there you go. Okay, so again, those were a little harder because we had to change the form before we could find the derivative. So I want you to do a problem like that. So change the form of the expression first, and then find the derivative. When you come back, we'll do it together. All right, we're back. All right, so if you got that right, good. So go ahead and try number 63. Remember, you have to change the form of those expressions before you can find the derivative. And when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, so let's do this one together. Now, notice that we're subtracting. We had a lot of problems where we had minus symbols. We didn't talk about differentiation formula number 5, which is just the subtraction version of this, because it's really just the same thing. And the reason it's the same situation is because you can consider, let's say that you have a function which can be written as f of x plus g of x. Let's say minus, so f of x minus g of x. Isn't it true that you can just change that expression, or you can consider it to be adding a negative expression? So rule number 5 is just the same as rule number 4. You're just adding a negative expression, so it's not really much different. Okay, so you can see we have a difference here. So we can use differentiation formula number 5. But again, this is just the same thing we've been doing. Now, students in calculus courses really get confused by fractions like this. But there's no reason to be confused. Before we take the derivative, let's factor the fractions out. And now we can see that this really isn't anything difficult. We're just going to use the constant multiple rule and the power rule. So you take the derivative and we get the following expression. I'm not showing every single step, but there you go. So that was technically using the 5th differentiation formula, but again, you can just think of it as adding a negative number, and then you're just using the 4th differentiation formula. So it's really just the same thing. So try number 65. When you come back, we'll do it together. All right, we're back, and there we go. So if you got that right, excellent. Try number 66. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, try number 67. When you come back, we'll do it together. All right, we're back. Minus 7/2 x to the 6. So if you got that right, perfect. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But don't go before you get your homework. So here's the first page of the homework, or first screenshot. And screenshot number 2. And number 3. And you have the homework answers. Make sure that your work is correct. If half your problems are wrong, then that means that the homework is just a waste of time. Any problem where you get the wrong answer is just a complete waste of time. So make sure that the homework is done completely and correctly, and I'll look forward to seeing you in the next class.